Right, so this last section here is actually talking about rational functions now. So we did quadratic functions in section 1. Section 2 and 3, we talked about how to find zeros or solutions of polynomial functions which were greater than degree 2. Of course, the last section, 3.4, we talked about how to graph these polynomial functions. Now this one here, we're actually introducing rational functions. So with rational functions, we're basically saying they're going to be ratios of polynomial functions. What that means is your numerator will be a polynomial function and your denominator will also be a polynomial function. It can have the form 1 over x, so that would be a very basic rational function. And then of course you can have where both my numerator and denominator are degree 1 polynomial functions, right? 2x minus 3 over x plus 4. As a definition for a polynomial function, we're basically saying both p and q are polynomial functions that are set up as a fraction, as a rational function. And since q is in the denominator, of course, we want to make sure that the value of q does not become 0. It does not become a 0 polynomial, because anytime you're dealing with rational numbers, you're dealing with fractions, division by 0 is undefined. So we can never have the bottom value becoming 0. So as you'll see, when we work through this section, we're always going to be conscious of that fact that anything that's making our denominator 0, we need to exclude those from our calculations. Now, the reason it's called rational functions is because anytime you can write an expression in the form of a over b, like a fraction, we call them rational numbers. If you were just doing 3 over 5, right? Those are rational numbers. When we use them as polynomial functions on the numerator and denominator, we call them rational functions. So they're saying that make the assumption that your function is going to be in lowest terms, which means there should be nothing common between your numerator and denominator, unless they tell us that it needs to be put into a reduced form. So by default, we're assuming that these functions are given to us as reduced expressions. Okay, so when we're talking about finding the domain for a rational function, since we're going to have our x variable in the denominator, there's going to be at least one number, which is going to make our denominator 0. So when they ask you for finding the domain of rational functions, you always take your denominator expression, set it equal to 0, and figure out what makes that expression equal to 0. So basically, if you look at your basic rational function 1 over x, since x is in the denominator, we know x cannot be 0. It can be any real number except 0. So in that same sense, let's see how the domain of this first example is going to work out to be. So we are given f of x equals x minus 1 over x squared minus 9. So as far as talking about the denominator goes, that numerator x minus 1 is going to have no effect on it, right? Just take your denominator expression and set it equal to 0. So since this guy is x squared minus 9, how do we solve it? What can we do? Yeah, you can go ahead and add 9 to both sides. You can try factoring if you like. Both of those will work. Okay, after we add 9, take a square root. So that gives us 1 positive, 1 negative root. And that will give us plus or minus 3. Yeah, 3. So there's actually 2 numbers that are making our denominator 0, because think about it. If I put positive 3 in there, that's going to be 3 times 3 is 9. 9 minus 9 is 0. You can try the same thing with negative 3. If we replace our x with negative 3, that's negative times negative becomes positive. 9 minus 9 is 0. So we know both those numbers make our denominator 0. So your domain is saying it can be anything from negative infinity to positive infinity, except it cannot use -3 or +3. So what will your domain look like then?
-infinity, -3.
Okay.
With the bracket, union, bracket, -3, -3, bracket, union 3, comma.
Okay, so if you're using brackets, that means you're
Or not,
including
or,
parentheses.
parentheses, yeah.
Okay. So except -3 and 3, everything else is okay. So I can use all numbers between -∞ and -3. I can use all numbers, of course, between -3, +3, and anything after 3 to +∞. All of those numbers are okay, except obviously negative and +3 themselves. So as Trey mentioned, we go from -∞ to -3, parentheses, union, -3 to +3, union, +3 to infinity, all with parentheses. Questions on one? How to find the domain? So this is going to be true for all rational functions. Take the expression on the denominator, set it equal to 0, solve it, and whatever numbers you get are the numbers we cannot use. Okay? Alrighty, let's see what's happening here. Now, the next thing we have to worry about when we're talking about rational expressions is what we have as horizontal and vertical asymptotes. Asymptotes, if you actually try to graph these functions, you're not going to see these lines. So they're basically imaginary lines unless they happen to fall on your x and y axes themselves. So these are imaginary lines, but the behavior of your graph makes it pretty evident of what is happening. So if you look at the graph for 1/x function, this is the entire graph here. On the right-hand side, they're just showing the partial graph here on the left. So you will notice that as this part of our graph on the right is getting closer to the y-axis, it's actually getting really, really close, but it's never going to touch the y-axis, and it's definitely not going to cross the y-axis. So your graph is going to get really, really close to the y-axis, but it never touches. And it's the same thing that's happening here on the negative side of the y-axis. Again, this arm of our graph is getting really close to the y-axis, but it's never going to touch. And just to show you, again, let's go back to our decimals here and take 1 divided by x. So this is what the graph looks like. Let's go up a little bit. And at this point, it looks like, you know, of course, our two lines are overlapping, right? The y-axis is actually with the graph itself, but as you zoom in, you'll start noticing that gap between the y-axis itself and the graph, which is in blue. Same thing's gonna happen on the negative side. So let's go down a little. And again, when you zoom out, it looks like, okay, the two lines should be coinciding, but same thing, as you zoom in, you'll notice that these lines are not touching. And you can do this for going into 1,000, -10,000, whatever is gonna have the same behavior. So that means for our function here, right at the y-axis, this specific graph, 1/x, has a vertical asymptote. So that means your graph will actually go towards +∞ or -∞, but it's never going to actually touch the line. It's never going to cross this line, which is your vertical asymptote. Here, you will also notice similar behavior happening with respect to our x-axis. So on the right here again, this arm of our graph is again getting really close to the x-axis, but it's not going to touch, it's not going to cross, and of course this arm here is going to go towards +∞. On the left-hand side, this arm, same thing, is getting really close to the x-axis on the left, but he's also going towards -∞. So we have both vertical and horizontal asymptote. In this graph, the vertical asymptote happens to be on the y-axis, the horizontal happens to be on the x-axis. And again, if you look at your little Desmos graph here with respect to the x-axis, So we're somewhere near 100, and you'll notice that same gap between your x-axis and the graph itself, okay? So that's the basic idea between what we mean by a vertical asymptote and horizontal asymptote. Now, not for all graphs, you're not going to have these asymptotes always at the x and y axes. If your graph changes, the location of your vertical and horizontal axes change. So actually, for this function that we just talked about, we could not use +3 and -3 in our domain, and the reason for that is we actually have two vertical axes for this graph, and one of them is at +3, the other one is at -3. So that's the correlation between when you're calculating the domain, you're actually also calculating the vertical asymptote at the same time. So where your domain fails for these functions is exactly where you have your vertical asymptotes. Now, of course, we'll talk about how to find the horizontal one for this guy. And these tables here are actually just showing you what's happening when you're getting really, really close. So this one here is talking about as we're getting really, really close to 0 from the negative side on our x-axis, our y values are actually headed down towards -infinity. So that's talking about this arm right here, which is going down to -infinity on the y-axis. On the other side, our x values are getting really close from the positive side, and now my y is headed to +infinity, so that's going to be this arm that's going up to +infinity, and you can do that same kind of checking with the horizontal asymptote. So the closer we try to get to the y-axis, to the y-axis, we are moving away. Okay, hold on a second. Sorry, we're getting closer to 0 on the y value, not the y-axis. We're getting closer to 0 on the y value, which means we're trying to get closer to the x-axis, and of course we start going towards -infinity and +infinity. Now, oh, and they're talking about the function 1/x having symmetry with respect to the origin because this is an odd function. I think we had actually talked about that in chapter 2. So just your basic definition for vertical and horizontal asymptotes. Vertical asymptote, of course, your x has to be approaching a number. In the example 1 that we did, those numbers would be +3 and -3. So as x gets closer and closer to those numbers, your y values will start hitting positive or -infinity. With the horizontal asymptote, that relationship, of course, reverses. Your y value starts getting closer and closer to a number, and your x will start going to positive or -infinity. So these a values that you're seeing are going to represent those horizontal and vertical asymptotes. Okay. So as I mentioned, for calculating the vertical asymptote, it's the same thing that we did for the domain. Take the denominator, set it equal to 0, figure out where your denominators are going to be 0 at. Calculating the horizontal is a little bit different. So horizontal here, we're saying if you have an expression that looks kind of like the 1/x, right? We've got 500/x, -3/x², 5/x³, 2/x - 5. You should notice for all of these, we have a number on the top, no x, and the denominator is where the x is, right? So it's a constant term on the top and an x expression on the bottom. All of these values will actually be getting closer and closer to 0 as x gets closer and closer to infinity. So let's put that to the test here. Let's use that first expression that we saw and see what happens. So what I'd like you guys to do is get out your calculators and figure out what is 500 divided by 999.
0.5005. Oh, it's just repeating.
Okay, so 0.500,
5 repeating.
and it'll keep repeating, right? All right, let's change that denominator now. Let's make it larger. So instead of 999, let's make it 9,999. So just increasing it by,
Just add another zero.
The front, add another zero.
add another zero in the front. What else? These zeros also increase, right? You have now 5,000 instead of 500. And of course, these guys will keep going. Okay. What do you think will happen if I add one more 9 to the denominator? 2 zeros in front and?
Add 2 zeros to the space in between.
In between. Okay. Now we're going to try and see if we can break your calculator. I don't know.
Mine only goes to 10 then.
As many 9s as you can.
This
Wait,
is a whole
before you
bunch
get
of zeros in
tired
front
of-
of it. And then 5.
A whole bunch of zeros?
And then 5. For 10.
Mine puts 8 zeros in front of it, and then 5.
8 zeros in front of it. Okay. So I actually put 22 9s in my denominator. So I am getting, and this is not really matching the expression we have here, but how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. These guys are 13, so that should be 1, 2, 3, 4,
Should you have
5,
12
6,
zeros?
7, 8, 9, 10, 11, 12, and then whatever. So why are we doing this? Just to see if our calculators work? I'm hoping they work, right? What are we noticing as our denominator got larger and larger? So just look at those decimal values. What is happening?
Our numerators getting smaller and smaller, but it's not everything.
Yeah, I mean, obviously, the only way you're going to get to 0 is if you had 0 divided by some number, right? But yeah, our value is getting smaller and smaller. So the larger our denominator becomes, the closer we're getting to 0, right? So that's actually what we're going to need to use when we're calculating our horizontal asymptote. So any expression that looks like this, where I have a constant term on the top and an x on the bottom, all of them, as x goes to infinity, this expression itself will actually start getting closer to 0. So all these rational expressions that you had here, 500 over x, as x gets really large, e is becoming a 0. Negative 3 over x squared, as x goes to infinity, this whole entire fraction is going to 0. Same thing with these two guys over here. As x gets really large, this whole expression is going towards 0. So that's one thing we need to keep in mind when we're calculating horizontal asymptote. So if these were our functions, all of them would have the horizontal asymptote at y equals 0. And what line is y equals 0?
It's just the x-axis.
Yeah, it's the x-axis. So all of these functions are like 1 over x, and they have their horizontal asymptote at the x-axis. But now what about something like this? So we've got x minus 2 over 2x plus 3, which means I have an x in the numerator, x on the denominator, right? So if my x in the denominator is getting large, then x in the numerator is actually also getting large at the same rate, which means I'm not going to be approaching 0 anymore because I've got x on the top and x on the bottom. So let's actually take a look at what happens. How do we find his horizontal asymptote? So let's look at x, and you guys actually have this calculation in your handout, and then we've got 2x plus 3. So with expressions like these, we always want to divide each term by the greatest value of x, which means the highest degree of x. So both of these are actually degree 1, because this is x to the first power, this is x to the first power, which means each term of our expression we're going to be dividing by x. Okay? Now we just talked about expressions like this, right? 2 over x what happens when x gets really large?
It's closer to 0.
Yeah, it's going to 0, so this guy will actually become a 0. Same thing's going to happen here with 3 over x. As my x gets really large, this little expression here is becoming 0. Now what happens when I divide x by x? Yeah, these guys will become a 1. X and x will cancel out, leaving us behind with that 2, right? So as x is getting really large, this first part of our expression will become 1, minus 2 over x became a 0. On the denominator, 2x divided by x basically gave us a 2, plus 3 over x became a 0. What's 1 minus 0? 2 plus 0. So that actually means this expression, this rational function, is actually going to start approaching 1/2 as all of these x values start approaching infinity, which means your horizontal asymptote is going to be at y equals 1/2. Okay? For these guys, with the 500 over x, your horizontal asymptote was going to be at y equals 0, which is the x axis. Okay? Okay, so when you have constant on the top, x on the bottom, for all those types of functions, you're always going to end up at y equals 0 as your horizontal asymptote. For functions that have the same x degree, because remember this guy was x minus 2 over 2x plus 3, and you can kind of look at it here in the handout. That's the same degree of the x value, right? X to the 1, x to the 1. These guys are actually always going to approach the coefficients of your leading term. So that's 1 from the numerator, and that's 2 from the denominator. So 1x, 2x, same degree of x, you're always going to be at the ratio of the coefficients of your leading terms. Okay? Guys like these are always going to be at 0, 2 over x, 3 over x, and you can kind of see that calculation that I just talked about, you end up at 1/2. Okay, so let's apply this knowledge that we just learned back into our example number 2 here, which is the same example that we did in example 1. So that should look familiar. So for example 2, we have f of x equals x minus 1 over x squared minus 9. Exact same calculation that we did for the domain. So vertical asymptote take the denominator part only and set it equal to 0. And it's going to be the exact same calculation that we did for number 1.
So does that mean that you have 2 vertical asymptotes?
This guy will have 2 vertical asymptotes, yeah. So I'm just going to go through this calculation quickly since we did this for example 1. Okay, so you should get your vertical asymptotes at x equals -3 and x equals +3. So these will be the vertical. Which, kind of helps us out because we will already be doing these calculations for finding the domain. So at the same time, we found the vertical asymptotes. Now for horizontal, in this case, it's a little bit different than the handout example we just looked at. Because I have x to the 1 on the numerator and x squared on the denominator, right? So my two x values don't have the same degree. I have a larger degree in the denominator. So when I'm trying to find the horizontal asymptote for this, I'm going to take my x minus 1 over x squared minus 9. And remember, we divide each term by the highest degree of the x value, which in this case will be x squared. So you're taking each expression and dividing it by x squared. What's going to happen with 1 over x squared?
Just think.
1 over x squared.
Oh, it just becomes zero.
This guy becomes 0. And what about 9 over x squared? Same thing, because as my x is going to infinity, both of these expressions will go to 0. Okay. On the denominator, what's happening with x squared divided by x squared? 1. It's going to become 1. Very good. And x divided by x squared on the numerator, I can cancel one of these x's with one of these x's, right? I've got 1 on the top. Yeah, I've got 1 over x left behind, but I also know e is going to go to 0, which leaves us with 0 minus 0 on the numerator, 1 minus 0 on the denominator. 0 divided by 1 is 0. So what's our horizontal asymptote going to be at y equals 0? Because this is a horizontal line, its equation is going to be y equal 0. And remember, guys, these are lines, because even though they are imaginary lines, they are lines, which means you have to write them as equations and not just as numbers. So whenever you write them, always write it as x equals whatever the number may be for vertical, and y equals for whatever the number may be for horizontal. Okay, questions on finding the horizontal and vertical asymptote for this line? So that horizontal asymptote calculation is going to always reveal a different answer based on what kind of function you have. Now you should notice that I also had y-axis, y equals 0, the x-axis is my horizontal asymptote here, right? Just the same as what I would have had for 3 over x, or what I had for 500 over x and all of those expressions. So what this is telling me, we can generalize this. If the degree of your numerator is going to be less than the degree of the denominator, you are always going to be at x-axis as your horizontal asymptote. So if the degree in the numerator is less than the degree in the denominator, y equals 0, or the x-axis is always going to be the horizontal asymptote. If the degree is the same between the numerator and the denominator, it's definitely not going to be x-axis, because remember what I told you, it's going to be the coefficient of your leading terms, so that's going to be 1 over 2 when you're talking about the horizontal asymptote, and we're actually summarizing that right here. If the degree is equal from your numerator and denominator, the horizontal asymptote is determined by the ratio of the leading coefficients. If the degree of the numerator is less than the degree of the denominator, then the x-axis, or y equals 0, is our horizontal asymptote. But what happens if the degree of the numerator is more than the degree of the denominator? Oblique?
Yeah.
Okay. All right, so let's see what happens here. We're saying some rational functions have a non-horizontal line for an asymptote. If it's neither vertical nor horizontal, we call it an oblique or a slant asymptote. We normally go with oblique. And you have to use long division or synthetic division to find these asymptotes. So let's take a look at what's exactly happening here in number 3. So our function is 3x squared minus 4 over x minus 1. Okay, so let's start by finding the vertical asymptote first. What are we going to do? What did we just talk about?
X minus 1 equals 0.
Which one?
Denominator.
Yeah, denominator, very good. And this guy, of course, is going to be pretty simple. What do we get? Yes. Yeah, x equals 1. So that's the vertical asymptote. Let's see what happens if we try to calculate our horizontal. So this is where we take the larger degree and divide each term by that larger degree. So that should be x squared in this case, and divide everything by x squared.
You'll get 0 as a denominator.
We'll get 0 in the denominator, okay? Because these guys will cancel out, leaving us behind with the 3. 4 over x squared will, of course, go to 0. 1 over x squared will also go to 0. For that matter, the degree on the numerator is less than the degree on the denominator. So this guy is also going to 0. So technically, we now have 3 minus 0 over 0 minus 0. 3 divided by 0 is what?
0.
Robert.
Doesn't make sense.
Yeah, undefined. You know, I'm going to start charging you guys $1 every time you tell me 3 divided by 0 or anything divided by 0 is 0. You could probably get pizza by the end of the day. Okay. No 0. Please be careful. All right, and here's actually the clue. You cannot have both horizontal and oblique in the same function. You can only have 2 asymptotes, vertical and horizontal, or vertical and oblique. So both horizontal and oblique will not happen in the same function, which of course, since we didn't come up with a horizontal asymptote, that means we definitely have an oblique one here. All right, so let's see how we can calculate that. Okay, so remember how they said you have to either use long division or synthetic division for this. So let's start by using the long division part first. Okay, so we're dividing 3x squared minus 4. And you know what? I'm actually going to leave space for our missing term. So that's 3x squared minus 4. Okay? And we're dividing this by x minus 1, because that was our denominator. So if I have 3x squared on the inside and only an x term here, what should I have in my quotient? And? Yeah, you need both 3 and an x, right? Because we need this to become a 3x squared. So I'm missing a 3 and I'm missing an x. So multiply 3x times x is 3x squared, and then negative 1 times 3x is negative 3x. Whenever we're doing long division, remember we need to subtract, which means we change our signs. This guy will become negative, and this guy will become positive. Which also means these guys will end up canceling out. I'm left with a positive 3x. Bring down that negative 4. Same question, if I have a 3x here and an x here, what should I have in my quotient? Yeah, so that would be a positive 3. Multiply again, 3 times x is 3x. Negative 1 times 3 is negative 3. Since we're doing long division, we need to subtract again. So change signs, this becomes negative. He will again become a positive. the positive and negative 3x cancel each other out. Negative 4 plus 3, negative 1. So this is our remainder. And this is our quotient. So if we had to rewrite this expression, we would end up getting y equals 3x plus 3 from the quotient. And then we had a remainder of negative 1. Since that's a remainder, you always write it over the divisor, just the remainder part. And this is just rewriting our original function by breaking it up into quotient plus the remainder over divisor format. As far as our oblique asymptote goes, it's only coming from the quotient. So that's going to be y equals 3x plus 3. So in my math lab, you will see that they will ask you to rewrite the expression. So that's where that first part is coming into play, 3x plus 3 minus 1 over x minus 1. And that denominator only goes underneath the remainder, not under the quotient, right? And as far as the oblique asymptote itself goes, it's going to be that oblique line, which is a positive slope, passing through positive 3 on the y-axis. So that's going to be our oblique asymptote for this function. So you can see we have a vertical asymptote at x equals 1 and a oblique at 3x plus 3. Actually, let's go ahead and take a look at what that graph will look like. 3x squared minus 4 over x minus 1. Okay, so that's 3x squared minus 4 divided by x minus. Okay, let's bring this back in. So actually, you can see at x plus 1 is where x equals 1 is where we have the vertical asymptote. So if I zoom out, you should notice that I will never cross that vertical line. I'm not sure how much you can see, but you will see we're just kind of following along that x plus 1 here and just following along that x plus 1 here. So again, we're really getting closer to that x. I keep calling it x plus 1, but positive 1. So that positive 1 line, we're again getting really, really close to it from the positive side and the negative side, but we'll never touch or cross it. Now, as far as the oblique goes, let's see if we can graph that so you can actually visualize the line. That was 3x plus 3. And you can see how our curved arm here is again getting really close to that purple line, but again, it's not going to touch it, it's not going to cross it, and that same behavior is happening here on the lower half of our graph, right? So that's your oblique asymptote, and it's just because it's a slanted line, it's not really a horizontal asymptote. So we have a vertical and a oblique in this case. So anytime the degree of your numerator is larger or greater than the degree of the denominator, there's no horizontal asymptote, you will have an oblique. So just as a summary, for the vertical asymptote, take the denominator, set it equal to 0, and solve it. For the horizontal asymptotes, if the degree of the numerator is less than the degree of the denominator, all of those functions are going to y equals 0 or the x-axis as the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then it's going to be the ratio of your leading coefficients, right, where your x terms are. If the degree of the numerator is greater than the degree of the denominator, that's the only time you will see an oblique asymptote, and we rewrite our function as quotient plus the remainder over divisor. And as far as your asymptote itself goes, it's going to be just the quotient. Okay, that's the only portion that we will need out of that. So any questions on this number 3? Okay. Alrighty. Which, of course, gets us into how can we use this information to help us graph rational functions. Now, rational functions, as you kind of saw with that Desmos demonstration that I just did, end up looking a lot different than any of the functions we have done so far. And these asymptotes are very, very crucial if we're going to understand what the shape of our graph is going to be. So as you can see the breakdown of the steps here, we always want to start by finding all of these asymptotes for our function. And even though they are imaginary lines, to help us graph a good function here, we will draw them as dashed lines, so at least we know where our graph needs to be going. We will check for symmetry, because if there is any symmetry, it helps us in our graphing. Find any intercepts, x-intercept, y-intercept, and then of course, as usual, we'll need some more points to help us out. So we're actually going back to that first example we did, x minus 1 over x squared minus 9. We have a lot of that information already on hand. We know what the asymptotes are going to be for this function. This is number 4. So if you go back and look at your examples, where was the vertical asymptote at for this function? Yeah, it was at x equals -3 and +3. So those would be 2 vertical asymptotes. This guy had a horizontal, obviously because the degree of the numerator is less than the degree of the denominator. Where was our horizontal asymptote for this guy? Y equals 0, which is of course the x-axis. So if we're talking about a graph for this guy, since you guys have a grid on your handout, what I would do is just a little, maybe a hair underneath the x-axis, kind of draw your dash line so you'll remember that we have a horizontal asymptote at the x-axis, because that's going to affect the behavior of our graph. Let me do this a little bit. Okay, so at +3 and -3, we have our vertical asymptotes. So let's say 1, 2, 3, 1, 2, 3. So again, at +3, you want to draw your little dash lines. Well, we don't really need an arrow on that. Bless you. And -3, same thing. Okay. We have horizontal asymptote here. Okay, so let's see if this graph has any x and y intercepts. Let's start with our x-intercept. We make the y value 0. So that would be 0 equals x minus 1 over x squared minus 9. So how can we go about finding an x-intercept here? What should we do to solve this equation right here? Any ideas? Get rid of that denominator. So multiply both sides by x squared minus 9. On the right-hand side, they will cancel out. What happens on the left-hand side?
0.
Yeah, 0 times anything is 0. What next?
Or add the 1.
Yeah, add the 1 and that's your x-intercept. So x equals 1, which means at 1, 0, we have our x-intercept, which will be right here at 1, 0. Okay. Now, where will be our y-intercept? Oh, no. Y-intercept means making our x value 0, so that would be y equals 0 minus 1 over 0 square minus 9. So what does that y-intercept come out to be?
1 over 9.
Yeah, because 0 minus 1 gives you negative 1, 0 minus 9 gives you negative 9, two negatives become a positive, and we've got 0, 1 9. But she's not a happy number, but as a decimal, what is 1 9? So we can at least know where, kind of roughly, to put our point at.
Like 0.1111.
Yeah, it's a repeating 1, right? So a hair of a hair above the x-axis, right? Because you're looking at 0.1 to 1/10 of a unit, which will be, if this is our 1, 2, 3, 1, 2, 3, this guy is literally going to be just above the x-axis. Okay. Now we do need more points if we're going to figure out what is the shape of this graph. So what kind of points can we use? We've got vertical asymptotes at +3, -3, so we probably want to know what's happening on either side of this asymptotes. I would use, we already know at 1 we have an x-intercept, so I would use +2, maybe +4, +5. Same thing here, -4, -5, -1, -2. Kind of try and see what's happening at those points. So at 0, we have 1 9, which is our y-intercept. At 1, 0, we've got our x-intercept. So those points are known to us. So we should probably try and do +2. At 3, we have the asymptotes, so +4, +5. On the negative side, -1, -2, -4, -5. So what do we get for +2?
-1/5.
-1/5, very good. Which will be -0.2.
+5 is 1/4.
+5 is 1/4. So a quarter. +4.
There's 3/7.
3/7, which will be as a decimal.
0.42857. And then it keeps going.
Keeps going, okay. Just to get an idea where we need to put those points. -1. -1/4?
Just 1/4.
Just 1/4?
Right.
Yeah.
Yeah.
Which is also a quarter. -2.
3/5.
3/5, very good. And 3/5, I should have left more space, is about 0.6. -4.
3/7.
Mm-mm.
Negative.
Is it negative 5 seconds?
It is -5/7.
Oh.
And as a decimal,
0.7142.
-0.714.
Mhm.
Okay, and -5.
Negative 3/8.
1/2.
For -5, not 1/2.
Negative 3/8.
-3/8, yeah. They are really horrible numbers as far as graphing goes because all of these are just going to be approximately where do we put them. And what's the decimal approximation for that?
Negative 0.375.
Okay. All right, let's see if we can try and make sense of this. So we're trying to do +2. And yeah, is that -0.2, so just there underneath the x-axis at +2. +4 is 0.428, I would assume about 0.5, so halfway. So that's gonna be about halfway underneath that. What was a quarter? Now, that right-hand side, since we know it's sandwiched between, kind of sandwiched between a vertical and a horizontal asymptote, that actually means this arm of our graph will get closer to this vertical axis and just kind of keep going down. It's not supposed to touch it or cross it, right? And then on the x-axis side, it will again get closer and closer to the x-axis, but not touch, not cross. So that's actually what's going to happen on that right-hand side arm. Did I do that wrong? I did, didn't I? Because that should be positive and not negative. Okay, hold on. That was not right. Because these numbers are positive and not negative, I'm graphing them on the wrong side. Okay, so let's get rid of that. Let's get rid of that. These guys should be on the positive side. So +1/2, +1/4, so this should actually be going this way. Because it was the 2 that was at the -0.2 or something like that. I don't have it written down. Yeah, it's the 2 that was at the -0.2. So the other guys were actually on the positive side, so they should be going up, not down. And then let's see, we've got -1 at a +1/4. So +1/4 somewhere over there. -2 is at 0.6. It's about halfway there. Right? So you're actually going up. And if you wanted to see more details, you can do halves to see again what those answers would look like. But we are crossing the y-axis here, crossing the x-axis here. So you're actually going to come down this way and hit the vertical asymptote on this side. You are crossing your x and y axes and going up here, and then these are the numbers that will start getting larger. So you are actually going to cross both the x and y axes in this case, as we saw with our intercepts. And then let's see what's happening on that other side.
Is it just going to do this?
-0.7 and -0.4. So -0.7 will be 3/4 of the way down here. And negative. So yeah, this guy will actually be going this way. And this guy We'll be coming down this way. It's a very interesting looking graph. So this is x minus 1 over x squared minus 9. So that's kind of what we should be seeing on our graph. Any questions on this one? Just very quickly, if you had to talk about the domain and range of this function. Well, we talked about the domain before, so we should know that, right? Can we verify the domain here? Oh, I guess we'll use black. Domain here, like we noticed before, we're going from negative infinity to negative 3. We're going from negative 3 to positive 3. And we're going from positive 3 to infinity. What can you say about the range?
So negative infinity is 0. Like not including 0. Union. Right?
Negative infinity to 0, union 0 to infinity?
But the center one includes 0.
Yeah, we
Oh,
actually
so
do
it's
have a 0, right? So it's all real numbers, even though this is a funky looking graph. You are actually hitting all the points on the y-axis, right? Even just within this section, we're not skipping any single y values, right? Even though the other two arms may be restricted by the asymptotes, the center part is actually still using all the y values. All right, good job, guys. Have a wonderful weekend.